The single most common thing that scares people away from machine learning? The math. I'd need a PhD, they say, and they quit before they even start. So let me tell you the truth. You need far, far less than you think. A small handful of ideas, each with a simple visual meaning, covers the vast majority of it. Let's demystify the math for good. Here's the entire toolkit on one slide. Linear algebra. How you represent and transform data, vectors and matrices. Calculus. How a model learns. Derivatives. And probability. How a model handles uncertainty. That is basically it. 3 families of ideas. And the secret is, you don't need the heavy machinery. Just the core intuition behind each one. Let's make every one of them click. Linear algebra. Part 1. Vectors. Start with the most fundamental object, the vector. It sounds fancy, but a vector is just a list of numbers. And almost everything in machine learning is one. A house is a vector. Square footage, bedrooms, price. An image is a vector of its pixel values. Even a word, as we saw, becomes a vector. In ML, data means vectors. And the magic is geometric. A list of numbers is also a point, or an arrow in space. 2 numbers, a point on a flat plane. 3, a point in a room. 1,000 numbers, a point in 1,000-dimensional space which you can't picture, but the math treats exactly the same. So your data isn't a spreadsheet, it's a cloud of points in space. And ML is the art of finding structure in that cloud. Why does that view help so much? Because similar things become nearby points, and learning a pattern becomes finding a shape in the cloud. A line that separates 2 classes, a direction that captures the variation. The instant you see data as points in space, half of machine learning quietly turns into geometry you can actually reason about. The one operation, the dot product. If you learn just one operation in all of this, make it the dot product. You take 2 vectors, multiply them element by element, and add it all up. One number out. That's the whole thing. And that single number quietly powers a huge fraction of all of machine learning. So what does it mean? The dot product measures alignment. How much 2 vectors point the same way? Pointing in the same direction. A big positive number. Perpendicular, unrelated. 0. Pointing opposite, negative. So really, it's a similarity score. How alike are these 2 things? That question is a dot product. And it's absolutely everywhere. The similarity between 2 embeddings, a dot product, a single neuron taking a weighted sum of its inputs, that's just a dot product between the inputs and the weights. Recommendations, search, attention, under the hood dot products by the billion. Master this one idea, and you've understood the engine's single most common move. Linear algebra. Part 2. Matrices. Next up, the matrix. If a vector is a list, a matrix is a grid of numbers, a whole table of them. But the powerful way to see it is not as storage. A matrix is a transformation. It's a little machine that takes a vector in and hands you a new vector out, moved, somehow. And the moves are intuitive. A matrix can rotate a vector, stretch or shrink it, flip it, or flatten it onto a line. Multiply your data by a matrix, and you've transformed the entire cloud of points at once, rotated it, squished it, reshaped it. Matrix multiplication is simply, apply this one transformation to all of my data, all at the same time. And here's the punchline that ties it all together. A layer of a neural network is, at its core, multiplying your data by a matrix of weights, and then bending it a little. The whole network is a stack of these transformations, reshaping the data step by step, until the answer is easy to read off the end. Linear algebra isn't a prerequisite for neural networks. It is what they are made of. Calculus. Which way is downhill? Now calculus, and you need much less of it than you fear. Forget the integrals. Forget the limits. For machine learning, calculus answers exactly one question. If I nudge this input a tiny bit, how does the output change? That sensitivity is the derivative. And that's it. That's the whole idea. Geometrically, the derivative is just the slope of a curve at a point. Steep slope. A small nudge changes a lot. Flat. Barely anything at all. A positive slope means the output rises as you turn the input up. Negative means it falls. The derivative is simply the curve's local steepness and its direction. Nothing more than that. Now scale it up. A real model has millions of inputs. Its weights. The gradient is simply all of those derivatives bundled together. One slope for every single weight. And taken as a whole, the gradient points in the direction that increases the error the fastest. So, which way is downhill? Toward less error. The exact opposite of the gradient. And that, which you've now seen more than once, is the entire story of how models learn. Compute the gradient, take a step the opposite way, and repeat. Gradient descent. The only calculus you truly need for ML is this one intuition. The derivative is a slope. The gradient points uphill. And all the rest, the libraries quietly handle for you. Probability. Handling doubt. The last pillar is probability. Because a good model rarely says definitely. It says 80% likely. A probability is just a number between 0 and 1, measuring how likely something is. 0, impossible. 1, certain. 0.5, a coin flip. Models speak in these, constantly. It's how they express honest confidence instead of false certainty. Two more ideas finish the kit. First, a distribution. How probability is spread across all the possibilities. The famous one is the bell curve. The normal distribution. Most outcomes cluster near the average, with rarer ones out in the tails. Heights, measurement noise, random errors. They all tend to follow that bell. It is the default shape of randomness. Second, expected value, which is just a fancy term for the long-run average, weighting each outcome by how likely it is. It's how you reason about decisions under uncertainty. What's the average result if I did this many times? Probability for confidence, distributions for the shape of uncertainty, expected value for the average. That's the whole probabilistic toolkit you need to begin. All of it in one loop. Now watch all the pillars work together in a single training step. An image comes in as a vector. That's linear algebra. It flows through the layers, each one a matrix multiply. More linear algebra. The output is a probability across the classes. That's probability. We measure the error, then compute the gradient to nudge every weight downhill. And that's calculus. Round and round until it learns. That is the entire mathematical heart of machine learning. In one sentence. Represent data as vectors, transform it with matrices, output probabilities, and improve with gradients. 4 simple ideas, working together in a loop. Not a PhD, just a toolkit. What you don't need. So what can you happily skip? You do not need to derive backpropagation by hand, prove theorems, or memorize integration rules. The libraries, PyTorch and the rest, do all the heavy lifting. They compute every gradient for you automatically. What you actually need is the intuition to know what a dot product means, why a gradient points downhill, what a probability is really saying. Understand the ideas and let the tools do the algebra. And here's the kindest part of all. Learn it just in time. You do not have to master any of this upfront. Start building. And the moment you hit a concept, go and learn that one piece. Right then. The math comes alive precisely because you can finally see what it's for. That is a far faster path than a year of dry theory with no purpose attached to it. So the next time someone tells you that you need to be a mathematician to do machine learning, you'll know better. You need 4 intuitions. Data is vectors. Matrices transform them. Gradients teach them. Probabilities express their doubt. Hold those 4 pictures in your head, and the math stops being a wall and starts being a set of tools you genuinely understand. So don't let the symbols scare you off. Behind every intimidating equation in machine learning is one of a small handful of simple, visual ideas. And now you've met every one of them. Subscribe for more such intuitive videos